Well, welcome everybody back to our monthly Third Thursday telecon with Dr. Andrew Westphal of the Stardust at Home program. And I believe today, Andrew, you're going to give a general update and perhaps there's some news in foils as well. Is that correct?
That's right.
All right, take it away, Andrew.
Okay, so quite a bit has happened since the last time we talked. I want to thank Mike for joining as usual. Really appreciate that. So let's see. So the first thing I want to report is on not on the foils, but on the aerogel. So we unexpectedly got some beam time on beam line 1102 at the advanced light source. So 1102 is a heavily oversubscribed beam line. They have they have about 5 times as many proposals for that beam line as they can accommodate. And we've been very fortunate in the past to get time on 1102 for doing analyses of all kinds, but especially for the interstellar dust work to do the analyses of interstellar dust candidates in aerogel. And the reason that beamline is important is that it's almost unique in the world in its capabilities, and it enables us to, first of all, identify spacecraft secondary ejecta, which is most of the impacts that we found in the interstellar collector from Stardust. And if we can identify those, then we can, or we can reject ones that are spacecraft secondaries, which are fundamentally not interesting. Then we can take the next steps and do much more sophisticated analyses. So we had 2 Pico keystones that we got from Johnson Space Center with 2 interstellar candidates in them, and we analyzed them on 1102. One of them turned out to be, it contains cerium, and cerium is one of the telltale elements that tells us that this is a piece of spacecraft. And the reason that that's true is that it turns out that the solar panels on the Stardust spacecraft, I shouldn't say were, they really are. The Stardust spacecraft is currently in orbit around the sun. We don't have it back. We have the samples back, but the spacecraft is still in solar orbit. Anyway, the solar panels are coated with a cerium-doped glass. And so there were clearly impacts on the solar panels, and the solar panels were in the field of view of the interstellar collector. And so we were able to identify that that particular one very easily, the cerium M line or absorption edge, and we could tell that this was a piece of glass from the solar panels. The second one was a little bit more puzzling because we didn't see anything at all in that sample, and we finally concluded that it was, although it looked a little bit like a track. In fact, we were just talking about that this morning. When you look at the image from Stardust at Home, it looks like a track, but I think we were fooled. It was not actually a track. It was a feature that looked like a track, but it was in fact associated with one of these numerous sort of divots that we find in the aerogel tiles that I think came from the manufacturing process. So we were fooled on that one, but this is the way it goes. You know, that we have to sort through a bunch of possibilities before we find the built candidates. So it's disappointing, but on the other hand, we made progress. And so those are 2 that we won't have to look at again. And we have 2 more coming. We also expect to get more beam time in the spring on 1102. I'm hoping that we're going to get to be able to analyze many interstellar dust candidates. And we may have to go to, because JSC is stretched pretty thin, we may actually have to go to Houston ourselves to go do the extractions. We'll have to see how things go, and depends on when our beam time is going to be. So that's that piece of news. And so Mike or Dan, do you have any questions about that?
Were these beam lines and these results just within the last month or so?
Last week. Let's see, when did we have the beam time? It was at the end of End of the week before last.
Okay. Yeah,
So
so this is really hot off the press.
Yeah, that's right. That's right. So
good to get the fresh update.
Sorry, say it again, Mike.
I say it's good to get the fresh update. It's nice to know.
Yes, right.
What got done there.
Yeah, right.
Is it a huge disappointment, or does it allow you now to sort of better guess at what each up and coming candidate might be?
So I don't think that this is going to tell us by itself. These results are not going to help us to sort through. I mean, we can't really tell in the optical images. We cannot distinguish secondary ejecta from interstellar candidates. And in the case of this thing that looked like a track, it really did look like a track. It wasn't until we looked at it from the side that we could see that, okay, we don't see a track at all. But for all the world, from the other angle, it really looked like a track. So I don't think this is just part of the process. It's going to be something that's going to take, as we all know, it's going to take some time. So not a surprise.
Okay.
Okay, so let me now turn to foils. And so we've been talking quite a lot about how to redo or take a different approach with the foils. And the fundamental issue that we recognize is that we have a lot of data. We have something like 400,000 images to go through, and we have dedicated dusters who are going through those images, and, for which we're very grateful. But it's a huge amount of data, and and because we're serving them up all at the same time, what this means is that it doesn't feel like we're making progress at a rapid rate. And the reason is because of the large amount of data. In order to get at least, let's say, 5 pairs of eyes, which is what we'd really like to have on every image, it's going to take a long time. And so in order to not feel like, but to make progress at a more rapid rate in terms of getting through the images, what we've decided to do is to take a different approach and divide up the data into blocks. So this is a little bit like what SETI at Home does. So SETI at Home takes chunks of radio telescope data and serves them out to volunteers to search, rather than serving up the entire data set all at once. And I think that's the mistake that we've made in the past. So what we want to do is to divide this up into chunks of, we're thinking on the order of 1,000 movies, and to have everybody focus on one or maybe several blocks of data rather than the whole data set at once. And then we thoroughly search those blocks and identify the candidates, and then we say, tick, we're done with that block. And that way we have much more rapid feedback to people, and we can learn faster. I think this is going to be a much better way to approach things. So we've done some testing. One of the things that we've talked about is to form teams, and have teams which will compete with each other to analyze blocks of data. And each team would be given probably not the same block of data to look at, but be given different blocks of images. So we did a test earlier, I guess it was early last week, or maybe it was early this week. No, it was early this week. I'm losing track of time.
It was last week.
To verify that we can have teams which can work simultaneously and that the data will still be good. And that test was successful. So we can do that. In other words, what we can do is have teams all log in with the same username, but several people working simultaneously. And it will still record the data correctly. That was what we were not confident about, but that seems to have worked fine. And so that's a hurdle that we have cleared to be able to implement this. So the next steps are to work out the software changes we need to make in order to have different blocks of data served up to different teams. And conceptually, it's very easy. In practice, things are not never quite so easy. But that's what we're working on now, is to figure out. That's the major tall pole, I think, in being able to implement this. And then Dan, I don't know if you want to talk about your idea about what those teams might be.
Yeah, so my job here at the Space Sciences Lab is more on the education side and doing outreach for the lab and getting the good science here in the lab out into the public, who really are the people who are paying for this research. So they should benefit from it. So one idea we had was having these teams be made up of probably high school classrooms, and also not only having them compete, but giving them some background and maybe doing a visit to the classroom where we do some educational programming, partner with the teacher, meet with the teacher first, figure out how does this fit into their classroom lessons and into the local standards, and then do a little bit of one-on-one with the students. And then assign them potentially to one of our faithful dusters like Mike here as a team lead. And then set a competition date where all the different classrooms are competing at the same time, with the potential of winners coming here to the Space Sciences Lab for a tour. So we would do this locally first, do it with some volunteer teachers who are willing to help us out and just see how this goes. But I think it'd be very exciting to sort of give back to schools and to educators in a way that is exciting, and also they're learning at the same time.
Mm-hmm. Right. So the other aspect of this, I think, is going to be very interesting, is that it turns out that there are two separate efforts in the community to automatically recognize craters in foils using software. And so one is at the Naval Research Lab, and then the other is Zach Gainsforth in our group. We've been working on this as well. Now, the idea is not to replace dusters, but to complement them. And in fact, it may be that there are all kinds of ways in which this could be symbiotic. So, for example, it may be that the best way to do this is to have an automated algorithm take a first pass at the data and high grade the possibilities, and then have human eyes, which I think are always going to be essential to look at and evaluate impact crater candidates. So, so having both of these things working at the same time, I think, could be really, really good. And so we might even set up competition, in a sense, between teams and robots. So a little bit like, we were just talking about this yesterday, a little bit like Watson on Jeopardy. You know?
Yeah. It'd be fun. Yeah.
Yeah, that's right. That's right. But I think there's no question about it that the algorithm is it may be fast, but it will always miss craters that are idiosyncratic, because you're training on a particular set of images. So the algorithms are probably going to be very good. Well, we'll see how good they are. We'll actually measure it, but they'll be good at recognizing things that are sort of common. But for things that, there might be an impact that's straddling a scratch or straddling a piece of dust that a human can easily recognize and that an algorithm would totally miss because it just hasn't been trained on it. These algorithms are extremely literal and, will only recognize things they've been trained to see. So by definition, they will not see things that are unusual. And so I think this could be really educational. And so we're proceeding on this, and we don't have a timetable quite yet because we're trying to work out what our tall poles are. But as you can tell, we're making progress, and things are happening to make this work. So So I think that's all the news I have at the moment. So are there any, Mike or Dan, do you have any other questions or comments?
It'll be very interesting to see if that algorithm works, how well it discerns these craters. I know myself, at least 70% of the shots I look at, I could pick out a feature that could possibly be a crater. But
yes.
70% doesn't do us any good. So I have to be more discriminating than that.
Yeah,
but
right.
That's going to be a challenge, I think.
I agree. I totally agree. Yep. Yeah. But, you know, one of the things that might happen is that the algorithm, maybe the most useful thing it can do is to reject fields of view that are really, you know, there are not, we may be able to train the algorithm to do things like, you know, identify fields of view that are really unambiguously empty. Right, so things like, you know, that have no scratches and no weird features and no gouges and so on, and have no craters, and then that will help humans to not have to waste their time on those kinds of fields of view. So there are all kinds of ways this could be approached.
Sounds good. I did have one other question. I was curious.
Yeah.
How many samples, going back to the aerogel, have actually been evaluated on the beamline?
Let's see. So total, since the beginning of the ISPE, I think we're now up to 40. I think these two are numbers 43 and 44, I think.
Okay. Well, good. That's actually more than I thought.
Yeah. Mm-hmm. Yeah.
And how many do you hope to do?
Well, so I guess what we hope to do, first of all, we still have not completely scanned the entire collector. I think we've got about a third of it left to go. We've been stalled in that for a number of years because the bottleneck at this point is beamline 1102. This is really the bottleneck in our entire process, not just for scanning, but, you know, for Stardust at Home as well. Those are not the bottlenecks in our process. So how do I answer that question?
Well, the reason I asked was I think there were a number of candidates that were just going to go into cold storage because it's just too risky to analyze them all.
Yes. So I think it's 15% of the collector has been moved from Johnson Space Center in Houston to the storage facility at White Sands in New Mexico.
Okay.
And that is a generic policy of the curators in Houston, the curators of the extraterrestrial sample collections. And it's a safety thing. And in the case of the foils, for both on cometary side and interstellar side, the foils and the aerogels, those tracks, you know, those foils and tiles, aerogel tiles, were pulled more or less at random, and that was on purpose. Wasn't quite. I think that there were a couple of the largest tracks in aerogel that were deliberately chosen to go to White Sands, but for the most part, that they were randomly chosen on purpose. And so those may not be touched for, who knows, 100 years? I don't know. You know,
right.
There's a high bar to getting those. It's possible to get those samples back, but there has to be a really, really good reason. And the reason they do that, I think it's very smart. You know, the reason you do that is that, you know, you never know when a category, I'm going to make it up, category 7 hurricane comes through Johnson Space Center and puts Building 31, which is where all the you know, moon rocks and all the extraterrestrial samples are housed and handled, you know, puts the entire thing underwater. I'm going to make that up, you know, I don't know. But the point is that Houston is not the safest. You know, if you're going to choose a place to curate the extraterrestrial samples, Houston might not be the first place you'd choose if you were just choosing it based on safety.
Right.
So neither would California, for that matter. You know. New Mexico's pretty good. You know, New Mexico's is subject to very, very few natural disasters. So so it's a smart place to house these things as a backup. So anyway, I don't know how long it's going to take. You know, I think our experience is that we had it's going to be something like 10% of the impacts in the aerogel. That's a very round number. Are actually interstellar in origin, we think. And so we have to, you know, for every one that we find, we have to look through 10, and that's a lot. So hopefully we're going to be able to do many more than 2 on the next run, and so that's why we want to really accelerate what we get out of Houston.
The number of candidates, though, was 70 something at one point. Is the number?
Oh, we've identified more than 200.
More than 200 candidates. Okay.
Yeah, but you know, as Mike will tell you, there are a wide variety of different confidence levels, right? So some of them are definitely tracks, no question about it, 100% track, you know, unambiguous. And then others are, well, that might be a track, or maybe it isn't. And all we have is that optical image, right? Or the stack of images that we have on Stardust at Home. And the only way we can really tell is by pulling it out in a Pico keystone and then analyzing it.
Got it. Okay.
So, yeah, I wish that there were a way that we could do the analyses, you know, without having to do the extractions. And I think we probably could analyze for cerium. So that would be one way to do it. But the other background is, and this is the more insidious one, is impact. These are secondary ejecta that come from the lid of the sample return capsule. So you had an impact on the SRC lid. It splashed material up into the collector. It comes from the same direction as the interstellar dust stream. And so from the trajectory point of view, you cannot distinguish them. And they are, and the way we recognize them is because they have aluminum metal. Aluminum oxidizes, as Mike knows, as a chemist, aluminum oxidizes instantly, right? And it's highly reactive. And so aluminum metal, I guess there may be examples in nature of highly reduced systems where you can get aluminum metal, I think maybe, but cosmochemically, there is no aluminum metal. Aluminum metal has never been found in any extraterrestrial sample, which is hardly surprising. And so we identify the SRC secondary ejecta by the presence of aluminum metal, and we can recognize it on beamline 1102 by doing this technique called aluminum zanes, where we scan a monoenergetic X-ray beam across the aluminum edge, and we can. It's easy to recognize metal, but we can't do it in any other way. We can't. They have to be in a Pico keystone to be able to do that analysis. At least, I should say, we haven't thought of a way to any other way. Maybe if somebody more clever than us can figure it out, that would be good. But we haven't figured it out.
All right, Mike. Any final questions?
No, that was a very interesting discussion. I'm glad for the update. I guess we'll just hold off on the next phase of aerogel for a while, though, from the sound of it.
Yeah, I think so. Right. Yeah. Yeah, I think, and we're going to be. Sorry, go ahead.
That's it. But I am looking forward to whatever comes out on foils.
Yeah, I think it's going to be fun.
Yeah.
Yeah.
Could be.
Okay, very good. Well, thank you very much. And I'll see you next month.
Sounds good.
See you again,
Okay.
Mike. Thanks.
All right, Dan.
Bye-bye.
All right.
Bye.
Bye.